All right. So just a reminder, this week, what you're going to be looking at, if you look on in the 4.7 tab in the classroom, you're going to be learning about something called, or finishing up something called, the sampling distribution of the sample proportion. It's a little bit like the sampling distribution of the sample mean from last week, but it can be a little bit more complicated, and I'm going to work an example today. And then when you go to the 4/9 tab, there's no lecture, okay? But you have two assignments due. You have homework number 4 due. So when you open up homework number 4, it's just 3 questions. And then you also have exam number 3. Okay, so when you load up exam number 3, looks like this is 4 questions, each worth 25 points. And after this lecture today, you'll probably be able to jump right in and give it a shot. So I encourage you to start it sooner rather than later. Okay. So here's the problem we want to work today, question 1. All right, and I have the chat box open up if anybody has any questions they want to ask, or you can load up your microphone and interrupt me at any point. Okay. All right, so here's the problem. Question 1. According to the Department of Education, college professors spend an average of 100 minutes per day lesson preparing, okay, with the standard deviation of 40 minutes. You guys think that sounds about right? A little bit, an hour and 40 minutes a day lesson prepping? The correct answer is no, that sounds way too low, because I obviously put in, a lot each day. So I hope you guys are laughing at these terrible jokes. But anyways, so suppose a random sample of 30 college professors is taken, all right, and the mean time spent lesson prepping is recorded. Okay, so all I'm going to do is I'm going to talk to 30 college professors, and I'm going to say, how many hours a day do you spend lesson prepping? How many hours a day do you spend lesson prepping? And after I talk to 30 of them, I'm going to compute a sample mean. All right, so that sample mean is this X bar, okay? And we don't know what it's going to be equal to. So we're going to define it as a variable. Okay, we're going to say X bar is equal to the mean lesson prep time from a sample of 30 college professors. And don't necessarily stress too much about copying everything down, because I am going to share these PowerPoint slides in the classroom too. Okay, so we know something from the CLT. Does anybody know what the CLT stands for? It's central something theorem. Does anybody remember that maybe from the lectures or anything like that? Well, it's okay if you don't. So the CLT stands for the central limit theorem. So what the central limit theorem says, because the sample size is greater than or equal to 30, because we talked to 30 college professors here, all right, the sampling distribution will be normal with, so it'll be normally distributed with a mean and what we call a standard error. Okay, so mu sub X bar is equal to whatever the population mean is. And if you look back in the problem, we're telling you right there that the population mean is 100 minutes per day. And the standard error, which we denote as sigma X bar, you take the population standard deviation, which is 40 minutes, and you divide it by the square root of n. So let me just get this. And that's the square root of 30. So let's grab our trusty calculators. So we're going to take 40 divided by the square root of 30. And this right here is our standard error. So I'm going to round this to just one decimal place. This is 7.3. Okay, so the next question asks, all right, this is the hardest part of these problems whenever you do them, this part, because the next question is going to be some type of probability question. And once you get to this point, it's just using your graphing calculator, which is pretty easy. So the next part says, what is the probability the mean time is between 90 and 110 minutes a day? So I want to find the probability that this X bar is between 90 and 100 minutes, 90 and 110 minutes a day. Okay. Now at this point here, I'm going to use my graphing calculator. Okay. So the option was normal. And does anybody remember what the 3 letters after were?
Yeah.
I'm going to pause and drink some coffee. Yes. Thank you, Danny. Normal CDF. And what you're going to do is you're going to do the lower value. I want to go from 90, comma, to the upper value, which is 110, comma. Then you put the mean, which we found above is 100. Then you put the standard error, which we just found here, which is 7.3. So when you go to do your exams, like your homework and your quiz submissions, just make sure you put this in the work so that I know what you did. So going back to my calculator, going ahead. Someone said something. They have a question? No, okay. You go back to your calculator, you're gonna hit second function distribution right here. You want normal CDF. The lower was 90. The upper was 110. The mean was 100. Standard error was 7.3. And when you plug this into your calculator, that's just going to be the probability. And it's going to be 0.8293 when I round it to 4 decimal places. So the only difference between these problems and the problems you had when you submitted your quiz is this part right here. Okay, this is the only different part. Just take the standard deviation and divide it by the square root of the sample size, and then that'll give you the standard deviation or standard error, as we call it, to plug into your calculator. All right, do you think you could handle a question like this on your exam this week? Yeah, it's just straightforward, same as the previous problems, just this divide by the square root of n. That's the big difference there. Okay, this next example here. All right, this next example is going to be the new stuff that you would have learned at the end of last week and a little bit of this week, okay? All right. Yes, I can do this one like super slow. Yeah, you got it. I can pause and drink some coffee too while I do this. Okay, so this is the new stuff. So I will go super slow here. All right. So the problem goes like this. According to the Department of Health, now I just made this statistic up, so don't take this as a true value. I made this up about an hour ago when I made this slide. Okay, so made up. According to the Department of Health, 40% of adults contract the flu at some point during the flu season. Okay, what this 40% here, we're going to take this as the population proportion of people who contract the flu. Okay. We're just going to assume the Department of Health is correct, and that's P, okay? Next question says, next sentence says, suppose a random sample of 400 adults, right, is obtained. So this right here is our sample size, okay? It's 400, okay? Is obtained in the proportion who contracted the flu at some point during the flu season is recorded. Okay, so now here's this question. All right. When I talk to 400 people, do I know exactly how many of them, and by extension, what proportion of them will have contracted the flu? Yeah, no, I don't know how many of the 400 are going to contract the flu. We'd expect 40%, right? But I don't know exactly. It probably won't be exactly 40%. So I define this variable, okay? This variable is called p hat, and what it is the sample proportion, okay? So what p and that little caret on top, it really is called p hat. That's not a joke, okay? So we're going to let p hat be the sample proportion in 400 adults who contract the flu, okay? What we know, and this is because the sample size is large, okay? And let me just pause for a second. What I'm doing here in this example is a lot like on your homework, question 3, part A, where it says describe the sampling distribution. Okay, this is a lot like this question here. All right, so because the sample size is large, the sampling distribution of p hat will be normal or normally distributed with, so that's the important part. It's going to follow that bell curve. Okay, so when something is, this is where these type of problems get a little weird because we're talking about a proportion here. Okay, but the sampling distribution of all the different proportions that we could take, okay, is going to be normally distributed, and we denote this mu sub p hat, which is a little bit like this right here, mu sub x bar, okay? But mu sub p hat, so the average of the sample proportions should be equal to the population proportion, which is this value up here, this given value here. And the standard error is just this formula here. It's the square root of p times 1 minus p divided by n. So you just have to follow this formula. So it's 0.40 times 1 minus 0.40 divided by 400. So let's grab our trusty calculators and do that. I'll move this over just a little. So we got to do this. We got to take the square root of 0.40 times, and then in parentheses, 1 minus 0.40, close the parentheses, divided by 400. And this gets me 0.0245. This is important, and please remember this. When you do these problems here, for this standard error right here, you need to go out at least 4 decimal places. So 0.0245. Okay. That's the hardest part of this problem right here, okay? If once you get this part here, the next question is going to fall right into place. It's going to be pretty straightforward, okay? So the next question says, if I take this random sample of 400 adults, okay, what's the probability that that proportion is greater than, and I have to just change this to a decimal, 0.44. All you have to do here is use your calculator. All right, this is equal to normal CDF, always, always, always. And I'll give you a hint for your homework and your exam. If every question you're not using the normal CDF to answer a probability, you're going to get it wrong. It's just always the normal CDF. No matter what the problem is, if it asks for a probability, you're going to use normal CDF, okay? So I want to be greater than 0.44. So that's the lowest value. And then what you're going to do, because you want to be greater than, you're going to put some ridiculous number like 99999. comma, the mean, which is 0.40, comma, and then the standard deviation here. And now when you go grab your trusty calculator for this, you're going to go second function distribution, normal CDF, and you're going to have to put in these values here. So 0.44, comma, some ridiculous number. The mean here was this value that we have, 0.40. And this is our standard deviation right here. And this is what you should see in your calculator. Like if you have a TI-83, you have to plug this in. And it looks like the answer is 0.0513 when I round it to the 4 decimal places. And that's how you tackle these problems, okay? I know it's a little confusing, but this right here is the key part. If you can do these calculations here, then it's just the normal CDF stuff, okay? All right, so what I'll do now is I'll stop the recording and then I'll answer any questions anybody has.